Hello everyone, in this video I'm going to walk you through how to analyze logistics locations for individual assignments. To solve this problem in Excel server, first you need to install Excel server following the instructions that I posted in the 2 app. The location of a company's facilities is very critical to its success. In fact, one of the most important elements in designing a company's supply chain is the location of its operations. There are typically three types of plant location methods for identifying potential sites for plants or other types of facilities, such as the factor-rating system, transportation method of linear programming, and centroid method. In this exercise, we will learn how to use a linear programming technique as a plant location method. One of the most powerful methods is to estimate the cost using a network of plants and warehouses employing linear programming technique. Transportation problems typically is a class of linear programming problem. So using this technique, we can search the location to minimize cost of shipping and units to M destinations or to maximize profit of shipping and units to M destinations. In this question, we have a production cost and then transportation cost information. So we need to search the location to minimize all the costs associated with its operations. To satisfy cost minimization objective, we will use a linear programming tool solver in Excel for optimizing several requirements and conditions. In this problem, Sycamore Plastics SP as a manufacturer, polyethylene plastic pellets used as a raw material by manufacturer of plastic goods around the United States. It operates for manufacturing plants that are in Philadelphia and Atlanta and St. Louis and Salt Lake City. Each plant has a different capacity and production cost as shown here in this table. Also, SP has six contract customers located in New York City, Birmingham, Tar Heel, Dallas, Spokane, and San Diego. Transportation costs between four plants and six customers are shown here in this table. Transportation metrics for this exercise shows the shipping cost for each route. For example, the cost to ship 1 unit per 1,000 pounds from Philadelphia factory to the customer's warehouse in New York City is $45. Also, we have a contract demand from each customer that SP has to meet in this yellow row. Based on this information, I construct the server model here for you. The first table is taken from transportation cost per 1,000 pounds. Right below row, I added a total demand as same as the table. And I also added a column for each factory supply based on its maximum capacity. Next, we need to construct cells for the solution cells of this problem, which are C28 through H31. So in Excel server, these cells should be selected by changing cells later. In this case, we have 24 possible transportation routes here by matrix format. These cells should initially be left blank when setting up the server model. After making Excel server work, the actual flows will be shown in these cells intersecting the factory rows to customers' warehouse columns. For like a first table, we need to add a total supplied units row for each customer warehouse. In Excel server, these cells should be set in constraint sections. Then we need to add a total shipped column for each factory. Cells I-20 through I-31 contains the total amounts that can be shipped from each factory, indicating how much is actually being shipped from each factory in the candidate solution. In Excel server, these cells should be set in constraint sections as well. In this table, I added a production cost column to calculate the total cost since we have to consider production cost in each factory to minimize the total cost of its operations. So cells J28 through J31 are the production cost of each plant. Next, total supplied is sum of all shipped solution in each customer's location by using some function in each column. It is equal to sum of all shipping solution in New York City. And then you can drag it to the right to calculate the sum of the all shipping solution each customer's location. Next, total shipped is the sum of all shipping solution in each plant location by using some function in each row. So it is equal to sum of all shipping solution in Philadelphia. And then you can drag it down to calculate the sum of all shipping solution in each plant location. Next, we need to construct cells for total cost calculation, which consist of the sum of transportation cost and production cost. So the total cost of Philadelphia to New York City would equal shipping solution unit times transportation cost for 1,000 pounds plus multiplying shipping solution and production cost. After fixing the column of production cost, you can drag it to the right and down whole cells. Last, the total cost shown in cell I40 is the sum of all these individual costs, which is sum of all these individual costs, the cells C36 through H39. So in Excel server, this cell I40 should be set as target cell for cost minimization objective. Now you are ready to run Excel server linear programming by minimizing the total cost. That includes the transportation cost and production cost. To do that, you need to select the data and then click solver from the Excel menu. It will pop up the solver pane. And then first you need to select the target cell. Cell objective is related to setting the target cell, which is the total cost cell, I40. And then next we need to choose the changing cells from the candidate shipping solution table. So second table is the changing cell. And then you are required to add the constraints that are related to supply and demand. So first we have to consider supply constraint. Each factory located in each city has its own supply availability. So the factory in Philadelphia has a 750 supply availability, and in Atlanta the factory has a 900 unit supply limit, and in St. Louis the factory has a 1200 unit supply limit. Lastly, in Salt Lake City the factory can produce 1030 units at the maximum level. Therefore, the units that each factory is able to produce in each cycle should be less than equal to factory supply. So total ship is less than equal to factory supply limit. Okay. Next, we need to consider customer's demand constraint here in this function. Each customer's warehouse located in each city has its own demand requirements. So we need to add the customer's demand requirements. So the customer in New York City has a 525 units demand requirements. In Birmingham, the customer requires a 415 units. In Terre Haute, the customer has a 925 units demand requirement. In Dallas, the customer requires 600 units. In Spokane, the customer has a 325 units demand requirements. Finally, in San Diego, the customer requires 400 units at the minimum level. Therefore, the units that each customer requires in each area should be larger than equal to demand requirement, since customer demand in each city can be larger than expected total demand. So this total shipped cell should be larger than equal to total demand. And then click OK. Finally, you have to make sure to set the min function in solver, since we have to identify the optimal solution for minimizing total cost in this case. Next two options needs to be set for solving transportation problems. First, set the solving method to simplex LP. Linear programming, this tells the solver that there are no nonlinear calculations in our spreadsheet. This is important because the solver can use very efficient algorithms to calculate the optimal solution to this problem if this condition exists. Next, the solver check the make on constraint variables non-negative box as a default. This tells solver that the values in our solution need to be greater than or equal to 0. And then if you run Excel solver, you will get the answer by minimizing the total cost for maximizing profit of shipping from 4 plants to 6 customers' warehouses. Click OK. So the final total cost is $1,056,770 for this logistics problem. Multiplying the amount shipped in candidate solution by the cost per unit of shipping and production cost over the particular route makes this calculation. That's it.